Our next speaker is Brittany Cymes, and her title is Variation in Nanophase Metallic Iron Particle Occurrence in exsolved space weather lunar pyroxene. A lot of words I don't know.
Thank you, Lysia. Can you see my screen and hear me just fine?
Yeah.
Okay, great. Hi, everyone. Today I'll be sharing some of our recent work involving nanophase iron particles in a space-weathered lunar pyroxene grain. So nanophase iron particles are a frequently encountered product of space weathering, as Jeff mentioned, on lunar material, and I study these particles and other space weathering phenomena using transmission electron microscopy, or TEM. To give you an idea of what nanophase iron particles look like in the TEM, to the right here is a dark field image of an olivine grain acquired on our STEM instrument. And at the edge of this grain, you can see a space weathered rim. And upon close inspection of this rim, you can see it's full of nanophase iron particles. So these particles have been found in the space weathered rims of both iron bearing and also non-iron bearing phases due to a combination of effects that elicit their development both in situ and ex situ. That's a separate talk. Today, I want to talk about the iron bearing phases specifically. And recently I've been reading about how olivine has been found to be more favorable for nanophase iron particle formation than pyroxene in laboratory experiments. And I'm curious if this is a chemically or structurally driven phenomena, or both. And is there a way to answer this question using returned samples? The primary limitation of natural samples being, of course, the inability to control the variable of exposure conditions. We simply don't know if two lunar regolith grains of different compositions received the same space weathering input, unless, of course, they're in the same grain, such as in prior work from our lab on chromite, ilmenite, and glass. But then you lose the structure component. So can we analyze two chemically distinct minerals, always guaranteed to be in the same place for the same amount of time, in the same orientation with virtually identical crystal structures? And the answer is yes. We can analyze pyroxenes, which are a very important rock-forming mineral on the moon, and they have a rather special cooling feature that we can use to address this question. Due to symmetry differences, which result in calcium incorporation, there's limited solid solution between the calcium-rich clinopyroxenes and the calcium-poor orthopyroxenes. And what occasionally happens during the cooling process is something known as exsolution. Using this phase diagram between orthopyroxene and clinopyroxene as an example, you can see that when a stable pigeonite solid solution cools, it reaches a univariate curve, and then the melt separates into two more stable coexisting pigeonite and augite phases. And this results in something that looks a little like this cross-polarized light image here. So there's our two phases. And as you can see in the center of this diagram, the augite lamellae form parallel to the 001 plane. So these chemically distinct domains are not random. They share symmetry components. So now we've got our second component of controlling our crystal structure. So we looked at one of these very interesting grains. We prepared a pyroxene from sample 71501 for analysis in the TEM using our FIBS SEM. You can see our final sample here in the secondary electron image. This pyroxene sample actually has two pyroxenes. The main target here labeled 1-pix, and adhered to the surface is our exsolved grain labeled 2-pix. We used energy filtered TEM to visualize the exsolution lamellae. FTEM is a parallel illumination technique in which only those electrons that have lost a characteristic amount of energy are used to generate the final image. So when we center an energy selecting slit on a characteristic calcium excitation feature, this yields this image you see here. So the more calcium rich phases are brighter. And then performing electron diffraction then allowed us to identify these two phases as pigeonite and 001 lamellae of augite. And you can see here next door is the unexsolved pyroxene grain, which was also an augite. Moving the sample then to our STEM instrument, so now we're imaging with a focused probe. We acquired high angle annular dark field, or HADF images. HADF is a Z contrast imaging technique that helps us better examine the space weathered rim, because here the more iron rich phases are going to show up brighter. So now we're going to flip our contrast from the previous image. And upon close inspection of the space weathered rim of the exsolved grain, you can see that fewer nanophase iron particles form in the augite lamellae than in the pigeonite lamellae. In addition, we see nanophase iron particles forming up to 175 nanometers deep into the grain interior of the pigeonite lamellae. We don't seem to see this trend in the adjacent unexsolved augite. It develops nanophase iron particles on the same order as the pigeonite lamellae, and we thought maybe it's a difference in the iron content that could be behind this textural difference we see in the exsolved grain. Okay, so let's take a look now at the composition. We next use the STEM's EDS detector to collect X-rays from these regions, from which we can reconstruct elemental maps. You can see here very nicely domains of augite and pigeonite based on segregation of the metal cations, magnesium, calcium, and iron. We also collected on the adjacent unexsolved augite crystal. We can also quantify these data, which yielded these nominal compositions plotted here in this ternary diagram. And you can see indeed the pigeonite lamellae have more iron than the augite. So was iron the answer, was more iron the answer to our nanoparticle mystery? To make sure, we then turned to electron energy loss spectroscopy, or Eels, and we discovered it was probably not more iron, but different iron. Eels tells us not just chemical information, but can tell us about the oxidation state of the elements. And in the STEM coordination, we can acquire what are known as spectrum images, where an entire Eels spectrum is acquired at each pixel in a given area, and this generates a three-dimensional data set. Taking a look at a slice of this data corresponding to the characteristic iron excitation edges, we notice dramatic shifts in the shape and onset of the iron L edge, which correspond to different oxidation states of iron. We found iron 2 in the pigeonite lamellae, iron 3 in the augite lamellae, and metallic iron in the nanophase iron particles. And using concurrent standards for iron, we can actually generate maps of multiple oxidation states from these spectrum images to have a better spatial idea of what's going on. And it's very clear here on the left that the pigeonite lamellae host dominantly iron 2 and the augite host dominantly iron 3. And when we map all the iron together with oxygen here in the center, you can see that the iron nanoparticles are indeed reduced as they anti-correlate with oxygen. So we think that this iron valency partitioning is likely the reason why different nanophase iron development is observed. And we think this is so because of work that Kathy Dukes et al. In 1999 published, where she space weathered a terrestrial olivine grain that had a rind of oxidized iron around it. And there was a slowed but eventual reduction of iron 3 to iron 2 and finally to metallic iron. And when we inspect the augite lamellae at the rim, we do indeed find more iron 2 there than within the bulk of the lamellae. So it is happening, it's just slowed. So we sort of answered our question regarding the influence of chemistry and structure on nanophase iron development, but also not quite. But in our search, we might have found something truly interesting. Regarding space weathering, it's clear that these exsolved pyroxene grains provide such a unique condition for understanding weathering products in natural samples, but we were certainly not expecting the oxidation state partitioning. It's not really heard of. Nonetheless, this was a unique example of a space weathered oxidized phase. And I'm not a petrologist in a strict sense, but my understanding is that until very recently, the moon was considered to be a uniformly reducing environment. However, recent findings of hematite, magnetite, and ferric iron in picritic lunar glasses, along with these pyroxenes, demonstrates that the moon still has some redox history mysteries. Thank you. I will take some questions if we have time.
We do have time if there's any questions for Brittany. This is really great stuff. I love those images of oxidation state of iron.
Thank you.
Yeah, I have a real quick question. So for the time-dependent reduction, do you think this is related to hydrogen?
I do think
slowly moving out, or
I don't know if it's hydrogen slowly moving out. I think it's because we don't see, there's no structural alteration of the material. We've actually measured the continuity of lattices across the interfaces to see if it was like a more impact related energetics phenomena. This does seem to be solely kind of maybe like a sputtering, like a slow reduction through removal of oxygen.
Okay, all right, thank you.
Mm-hmm.
Maybe one more question.
I've got one.
This is John Rask. Brittany, did you do any particle size measurements to determine if there's any particle size effects?
So the particles in the pigeonite lamellae are they max out at about 10 nanometers, and we do get more fine population distributions in the augite. So they're very fine and very small. So I think that their formation is simply slowed because of the higher oxidation state of in the augite.
Well, thank you for your talk.